This will drive the high current magnets of Ilumi, which are the quadrupoles, the niobium-13 quadrupoles, plus niobium tie magnets, which are also installed for Ilumi. So the magnets...
They're the high Lumi specific.
Exactly. These are the magnets which are part of the high luminosity upgrades and which are located in the triplets at point 1 and at point 5.
Okay. So all the normal dipoles are just going to be run off the...
They are the biggest one are the final focusing quadrupoles. These are the magnets that provide the final focusing.
Is that for Atlas or was like...
For Atlas and CMS.
Okay, so there's going to be some at point 5.
Some at point 1 and some at point 5 indeed. And these magnets will have a new technology which is niobium-13.
Okay.
Yeah. These are strong magnets which provide a strong focusing in a relatively big aperture.
Amalia meant triplet magnets, so they will get then 10 times more radiation, and therefore we need to have a new technology. New technology is 10, and we have right now in the existing machine 9 Tesla, and that's at the limit of niobium tie technology. Okay. And with the new technology we go up to 12.
Okay, and then this is the line that feeds those magnets.
Exactly.
Okay.
To be more precise,
I'm assuming these are in series with the magnets?
yeah, no, that is absolutely right. I think what they actually, this is a DFH.
HX.
It's an X, so this is for the triplet.
For the
Okay.
triplets,
Yeah.
yes.
I was just thinking because they have 2 types. So one that feeds a triplet and the other one that feeds other magnets. But this is then actually the one that feeds a triplet.
Triplet is...
So, I'm sorry, these are the focusing quadrupoles right next to the detector.
Okay.
And we call them triplets because there are 3 functionalities: focusing, defocusing, focusing. And therefore it's 3.
So I was like, are there 3 magnets? Because I would assume
And
2
there are
magnets.
also
No, they're 3. They're 3.
So there are 3
They're
magnets
actually,
inside one of
to make it more confusing, there are 4.
Okay.
But the middle 2 have the same functionality. So they're
So
as
we
one.
have one tube that has the large aperture.
They all have the same.
And inside the tube you've got 4 sections that are different magnets.
All of these 4 magnets have the same big aperture, and they're all filled with the tungsten beam screens to absorb the radiation.
Yep.
But the first one is focusing, the next 2 are defocusing, and then the last one is focusing again.
Okay, so there are actually 4 magnets inside one cryostat? Or
No, there are
are they
4
in their individual...
4 different cryostats.
4 different cryostats, okay.
To make it more complicated, if you want to get complicated, the first and the last magnet is one cryostat, but there are 2 magnets in one cryostat.
Okay.
So if you want to count it like that, then they're
No,
actually...
I'm just like, am I thinking of one large...
pump it or anything, and if you think about height differences, it becomes very, very difficult. And this is beautiful.
Yes.
You just from the lowest point, you let the gas just go up. And,
You could not, in the tunnel you have a vertical path, you could not do it with liquid, but the beauty of this
because
system,
of the hydrostatic pressure then. And then because you
also-
can't pump and then valves get terribly
Exactly.
difficult and everything tends
and
to
also
be...
you need an homogeneous distribution. We have funny shapes, and superconductor wants to be in the cold. If it is outside of the liquid, in particular if it is conventional superconductor, it becomes critical. But the beauty of this system, as Oliver was saying, is that from the point of view of sustainability and cooling, the design is such that all these snake cost 0 in terms of cooling, because we would need that gas in any case for cooling the leads. So if you would have the leads close to the magnets and you would take the gas for cooling them, you will use the same amount of helium that we use by adding the link. So the secret behind is that there is a cryogenic optimization relying on higher operating temperatures, which makes the link basically being a transfer line, but not costing anything from the point of view of cryogenics. And to do this, we had to develop a very efficient, flexible cryostat.
Yeah, no, I was wondering like, oh, this is a cryostat? This looks...
It was a specific development supported by Ilumi.
Because initially we wanted to go about 100 meters vertically. We wanted to have everything, power converters on the surface, and then go down by 70, 100 meters. And Only that technology would allow you to do this. We changed it in the end for various reasons. but
One thing I did.
When you move from room temperature into the cold, the other step. There is a step where indeed you also need water cooling because everything which is high current is heavy and it also perturbates it. It tends to go in the cold. So you have to do
I'm
this
assuming you're going to
carefully.
have like a lot of magnetic field through here if you're going to push 18 kiloamps.
But to come back to your
It
question,
decay very fast.
so what Amalia developed for the existing LHC, very important, is the transitions of this to the 1.9 Kelvin inside.
Okay.
Yeah.
And this is high temperature superconductors which are in steps first cooled by nitrogen,
Yeah.
I think.
So
And
we
then-
use
Oh, so you
in
use like
this-
multiple different technologies,
Exactly.
like and put them.
So we have multiple
Okay.
from room temperature to 50 Kelvin. We do it in a special way with copper, but it has to be special. If not, you bring to it down. Then we go down from 50 Kelvin down to 20 Kelvin with Repco, which is probably the superconductor with which most of the people are familiar because it works also at liquid nitrogen. And then we and you see typically levitation experiments.
Oh, that's okay.
Okay, in the form of tape, not a bulk tape. And then from 50 Kelvin from 20 Kelvin to 4.2 Kelvin, we use magnesium diboride, which is also a new generation of superconductor that we developed for Elumi and that we use for the first time in large scale for big power transmission cables.
Okay. And
So we
this
have
is one of these big power transmission cables.
Then
I'm
GV2
assuming-
is there, it's
Yeah.
all inside that.
And I'm assuming, like from what I saw, like the power what? Can you show me the cable? Like, do you have like I saw
When
like
it
something
comes
over.
out from the other side, we can show you the cable.
No, but I mean like
Once you also see
there's
when
a
they-
sample
when they unwrap it,
like
you
that's
actually
unwrapped
see
the
after
different.
you see
We can-
water cooled.
Everything big is water cooled because if not, the cross section would be too big. Bigger, we mean 1 kiloampere and beyond.
So how much goes through one of these cables? Do you-
18 kiloampere.
No, one of the black ones.
One of the, I think that
I would-
they
I
are
would guess
divided
six.
by a group of
I would think 6.
Let me check this one. I think 3 kiloampere.
Yeah, so it's 3 or
About 3 kiloampere.
3
yeah.
kiloampere per
2 to 3
cable.
kiloampere per cable. Yeah.
And that goes in here, and I'm assuming this is like a bus bar.
This is a distribution, an electrical distribution box.
And then I'm
And
assuming
then this is
something
warm.
goes.
Then we will ask you if you can we have a special equipment which will make the transition from warm to cold. Inside a cryostat, these are for current.
So it's like, and I'm assuming if you would like take a large block of copper like this and like connect it to your
current.
superconducting.
It doesn't work
That won't work because you're going to drain all of the.
because that is cold
Yeah.
and this is warm.
Yeah. And
The magnesium diboride is only the small
like the
cables
thin-
around it.
And there is also a reason for that
I'm
because
assuming the core is because of quenching.
Stability and
being a bus bar, it has to be super safe. So there is a significant amount of copper to bypass in case of quench. So it's a compromise in between the weight, because nevertheless these things have to be handled, and the maximum safety that you can bring in the system.
but it's also, I mean, magnesium diboride, correct me if I'm wrong, it's also brittle. So if you would pull on this without the copper in it, you would
Is
break
it, is
it.
it similar to the
Yes, we have a Kevlar also inside. But this is important that while Repco exists, the Repco superconductor that we were saying we will use in the first transition is very expensive, and we use it on a short length because if not, the project would not have approved. We would not have even dared to ask the project to approve it. Because the cost of the conductor cannot be more than, say, 20% of the global system, if not, it has no sense. So we developed specifically bipolar with the industry, MGB2, which at the time was not yet available in the form of a round wire. And we wanted to have a conductor which was already reacted and could be cabled already reacted with sufficiently good mechanical properties.
Okay.
And this
Reacted means that you've somehow coated the copper core. in the
Reactive means that when you buy an niobium 3 tin, you buy something that they sell to you as a superconductor, but it is not superconducting.
because you have to cook it and then
Because it's so brittle that you have to cook it after.
so you wind it into the coil
and then you cook
stabilize
it,
the coil
yeah.
and you cook it.
Okay, so once you treated it, right, you cannot wind it anymore. It's not a ceramic, but it's like a ceramic. You cannot move it anymore.
Okay, so like if this cable is installed, it cannot
No,
move. or can
this
barely-
is for niobium-3 tin. For
Okay.
the magnesium diboride,
For the magnesium,
You-
we
you can
developed
still-
a wire which was
Still
sufficiently good mechanically and electrically speaking to be industrialized for cabling, because the
Okay.
first cables were R&D, but now it's a big company which
Okay,
is...
so yeah, so it's one of these CERN industry partnerships. That,
and
so this
for
is
the production, not for the development.
so this,
No, I'm-
this is much nicer for the mechanical behavior because you can bend it slightly, but it doesn't resist very well magnetic fields, ambient fields. So that's why you cannot use it in a magnet.
yeah, I was wondering, like, if we go to all of this work
Be
with
careful
the
on
with
the
the,
other. Yeah. So there is a R&D for pushing it to higher field because it has an upper critical field which is high. If you measure the single crystal, the upper critical field is more than 30 Tesla. But then when you make a wire, it's today it's not possible to exceed to have reasonable current for fields more than 45 Tesla.
So is this-
there is a R&D to be done.
so is this
eventually.
something similar to like you have lots of these crystals inside the metal structure,
Yeah.
and then for every crystal this would be
Yes.
30 current, but
Yes.
because we have like millions of crystals along the length of the wire.
Exactly.
Okay.
So for instance, for the Repco, since you know about the crystal story, the Repco is a material that we use at low field, but it goes also at very high fields.
Okay.
And this is because when the process which makes the Repco deposit the crystal in such a way that you have a biaxial texturing, and you optimize the transfer of the current in the favorable direction. But in order to get that, so this means that you cannot have a biaxial texturing if you have a round wire.
Okay.
Because if you
It
put
needs
a
to be a
powder
flat-
and then
needs to
you
be a
draw, the crystal have any direction. So the consequence is that the Repco is extremely expensive because you rely on a deposition technique
Oh, you
where
need to make the entire crystal kind
you
of.
put
Is this-
exactly.
Is this a
Exactly.
monocrystal? Is this a monocrystalline?
It's not a monocrystal, but you have to put basically
But you have to kind of grow it in a
atom by
particular-
atom on an already texture substrate. It's not
and then you
doesn't
have to
matter
texture the
what.
substrate, and
You
this
have
is all
to texture the
nanoscale, so it's gonna be
substrates in order to, because 1 or 2 degree of tilt, the material is gone.
Okay.
But maybe the nice stuff which liquefies the helium. Again.
For a
It's
power
not a big deal.
transmission line.
And so
When
the
it was
cross section is
director
like.
in German,
I would really
Germany,
like to see the cable.
It was
This.
an
I'm
honor,
assuming
yes.
because the cable looked pretty thick.
Amalia will show you.
Okay.
She should.
See it because you see it when they unwrap it, you actually see the compounds of the cables. I think
Yeah, that
the
would be-
Actually,
kilo
it's
and
nice.
cable
We
is
can have
probably
some
that,
nice. We don't have professional people.
To the magnets anyway.
As we do it right now. So we have right now water-cooled cables that go all the way to links that we discussed before with the liquid nitrogen and all of that. But they consume, ballpark figures, a few 10 kiloamps. If you do this for the whole new system, you talk about hundreds of kiloamps that you just
Yes. I think we
cool
should
away
also say
all the
that
time.
it's,
It's a waste of energy.
So okay, so if you so
Sustainability.
let me rephrase that so I understand you correctly. If you have add up all the links, you're talking about hundreds of kiloamps that you have to bring to the magnets, which will drop voltage and therefore lose power on the way to the magnets, which we obviously need to cool, and that link uses essentially the exhaust gas, so to speak, of the divars at 2 Kelvin anyway, runs all of the current through this thing that you're gonna need to pipe the gas out. You can run all of the links to
Just
there.
make it longer.
And then we can take some pictures
Okay,
of the
but you
cable
save
as it
tens of
comes out.
Yeah. No,
Kilowatt, huh?
I see that immediately now, but that was kind of I wasn't
Yes,
quite sure.
thank you.
Okay.
Sure. With Repco is that the material itself, therefore, is not the driving part for the price. It's a process.
It's about, and you
So,
can probably
and there you can have the hope that with industrializations you might get to a stage where the cable becomes much cheaper if this can be
Yeah.
industrialized.
okay, and if this can be made reliable
Yeah.
and repeatable.
But
So that's the hope for
yeah.
the high field magnet development and all of that.
Absolutely. And for power transmission, if you would have a Repco chip, then you rely on liquid nitrogen. Not for us because we are special. But the So the next step is that they will fully cover. And move from room temperature into the cold.
Sure.
The other step. There is a step where indeed you also need water cooling because everything which is high current is heavy and it also perturbates it. It tends to go in the cold. So you have to do
I'm
this
assuming you're going to
carefully.
have like a lot of magnetic field through here if you're going to push 18 kiloamps.
But to come back to your
It
question,
decay very fast.
so what Amalia developed for the existing LHC, very important, is the transitions of this to the 1.9 Kelvin inside.
Okay.
Yeah.
And this is high temperature superconductors, which are in steps first cooled by nitrogen,
Yeah.
I think.
So
And
we
then-
use
Oh, so you
in
use like
this-
multiple different technologies
Exactly.
and put them...
So we have multiple
Okay.
from room temperature to 50 Kelvin. We do it in a special way with copper, but it has to be special. If not, you bring to it down. Then we go down from 50 Kelvin down to 20 Kelvin with Repco, which is probably the superconductor with which most of the people are familiar because it works also at liquid nitrogen. And then we and you see typically levitation experiments.
Oh, that's okay.
Okay, in the form of tape, not a bulk, tape. And then from 50 Kelvin from 20 Kelvin to 4.2 Kelvin, we use magnesium diboride, which is also a new generation of superconductor that we developed for Elumi and that we use for the first time in large scale for big power transmission cables.
Okay. And
So we
this
have
is one of these big power transmission cables.
Then
I'm
GV2
assuming-
is there, it's
Yeah.
all inside that.
And I'm assuming, like, from what I saw, like the power trans, like, what? Can you show me the cable? Like, do you have like? I saw
When
like
it
something.
comes
over-
out from the other side, we can show you the cable.
No, but I mean, like,
Might you also see
there's
when
a
they-
sample
when they unwrap it,
like
you
that's
actually
unwrapped
see
with
that
the
there
different.
is-
We can-
With Repco is that the material itself, therefore, is not the driving part for the price, it's a process.
It's about, and you
So,
can probably
and,
and you can,
and there you can have the hope that with industrializations you might get to a stage where the cable becomes much cheaper if this can be
Yeah.
industrialized.
okay, and if this can be made reliable
Yeah.
and repeatable.
But
So that's
for-
the hope for
yeah.
the high field magnet development and all
Absolutely.
of
And for power transmission, if you would have a Repco chip, then you rely on liquid. Not for us because we are special. But the
that.
Repco,
Magnesium diboride is only the small
like the
cables
thin-
around it.
and there
Okay.
is also a reason for that.
I'm
because
assuming the core is because of quenching.
Stability and
being a bus bar, it has to be super safe. So there is a significant amount of copper to bypass in case of quench. So it's a compromise in between the weight, because nevertheless these things have to be handled, and the maximum safety that you can bring in the system.
but it's also, I mean, magnesium diboride, correct me if I'm wrong, it's also brittle. So if you would pull on this without the copper in it, you would
Is
break
it, is
it.
it similar to the
Yes, we have a Kevlar also inside. But this is important that while a Repco exists, on the Repco superconductor that we were saying we will use in the first transition is very expensive, and we use it on a short length because if not, the project would not have approved. We would not have even dared to ask the project to approve it. Because the cost of the conductor cannot be more than, say, 20% of the global system. If not, it has no sense. So we developed specifically high power with the industry MV2, which at the time was not yet available in the form of a round wire. And we wanted to have a conductor which was already reacted and could be cabled already reacted with sufficiently good mechanical properties.
Okay.
And this
Reacted means that you've somehow coated the copper core. in the
Reactive
mag-
means that when you buy an niobium tritin, you buy something that they sell to you as a superconductor, but it is not superconducting.
Oh, because you have to cook it and then
Because it's so brittle that you have to cook it after.
so you wind it into the coil
And then you cook
stabilize
it,
the coil
yeah.
and you cook it.
But also once you treated it, right, you cannot wind it anymore. It's not a ceramic, but it's like a ceramic. You cannot move it anymore.
Okay, so like if this cable is installed, it cannot move. or can
This
barely-
is for niobium 310. For the
Okay.
magnesium diboride,
For the magnesium,
You-
we
you can
developed
still-
a wire which was
still
sufficiently good mechanically and electrically speaking to be industrialized for cabling, because the first cables were R&D, but now it's a big company which
Okay,
is
so yeah, so it's one of these certain industry partnerships that.
and
so this
for
is
the production, not for the development.
so this,
No, I'm-
this is much nicer for the mechanical behavior because you can bend it slightly, but it doesn't resist very well magnetic fields, ambient fields. So that's why you cannot use it in a magnet.
Yeah, I was wondering, like, if we go to all of this work
Be
with
careful,
the with
otherwise
the,
you're- yeah. So there is a R&D for pushing it to higher field because it has an upper critical field which is high. If you measure the single crystal, the upper critical field is more than 30 Tesla. But then when you make a wire, it's today it's not possible to exceed, to have reasonable current for fields more than 45 Tesla. So there is R&D to be done.
So is this something similar to like you have lots of these crystals inside the metal structure, and then for every crystal this would be 30 current, but because we have like millions of crystals along the length of the wire.
Exactly.
Okay.
So for instance, for the Repco, since you know about the crystal story, the Repco is a material that we use at low field, but it goes also at very high fields.
Okay.
And this is because when the process which makes the Repco deposit the crystal in such a way that you have a biaxial texturing, and you optimize the transfer of the current in the favorable direction. But in order to get that, so this means that you cannot have a biaxial texturing if you have a round wire.
Okay.
Because if you
It
put
needs
a
to be
powder
it
and
needs
then
to
you
be
draw the crystal have any direction. So the consequence is that the Repco is extremely expensive because you rely on a deposition technique.
Oh, you
where
need to make the entire crystal kind
you
of.
put
exactly.
exactly.
Is this a
Exactly.
monocrystal? Is this a monocrystal?
It's not a monocrystal, but you have to put basically
But you have to kind of grow it in a
atom by
particular-
atom on an already textured substrate. It's not
and then you
doesn't
have to
matter
texture the
what.
strap plate, and
You
this
have
is all
to texture the
nanoscale, so it's gonna
substrates
be-
in order to, because 1 or 2 degree of tilt, the material is gone.
Okay.
But maybe the nice